voltage, like from a utility. The utility lines overhead are usually 4160 or 12470, 12,470 volts. Well, your house is 240 volts. You know, so it goes from, let's say it goes from 4160 down to 240. So that's a huge drop in voltage, and you can go from a larger wire to a smaller wire, but your current, you got to worry about your current now, because when your voltage is dropping, your current's going up all the more. And that's why transformers for utilities have multiple secondaries. So one transformer might feed 20, 30 homes. And so it keeps tapping off the secondary, and the total current is equal to the sum of the individual secondary taps. Now this ratio right here, V secondary to V primary, is given the term, the Greek letter nu is called the turns ratio. The turns ratio. I have seen it in books where the turns ratio is V primary over V secondary. They flip it. I don't know why, but in this text, the turns ratio is defined as the voltage on the secondary divided by the voltage on the primary. Okay, these are pretty much the formulas you want to be looking at. And you could easily derive these formulas the way I did. Just remember, power in equals power out. Voltage times current equals voltage times current. Do your algebra, you're done. You got it. There's one other formula that that's in the book, and that's called the mutual inductance. The ability of the transformer to affect on the secondary what's happening on the primary. We call that mutual inductance. And that goes by this designation, and it is, here's the formula. So this is sort of like a formula that it has to do with the efficiency of the transformer as a system, if you will. This would be the inductance of the primer of one coil, the inductance of the other coil, and this is known as a coupling coefficient or a coefficient of coupling, one of the two. So this guy here would have a very low mutual inductance. So if I connect this larger coil to a source and expect to get a whole lot of energy out of the secondary, it isn't going to happen. Very low mutual inductance, okay? Just because of the geometry, the coils are not that close together. Even though that is a transformer, technically. So a transformer, the symbol is it's just two inductors with those double lines. Those double lines means that it's an iron core. Okay, I mean that's chapter 14 is, I mean, when you get past those formulas, there's just not a whole lot there. They give you applications and a few problems here and there, troubleshooting problems, but there's really not a whole lot there. Transformers is something, and even in 30 years as an engineer, I mean, with those formulas, that pretty much says it all. You can't get much beyond that. Unless you get into the business of unless you actually work for a company that designs transformers, that's another, then that's another ball game right there. Then it really gets complicated. So. Okay, who has questions? All right, let's do one more lab, and then we're out of here. Let me see, I just want to make sure this should be fairly easy. Okay, let's do this one. Everybody turn in their homework if you got it. Your homework. And also your other labs. Alrighty, alright. These, your other labs? You're not done yet?
Just, it is supposed to be yes.
Got your name on it and all that good stuff. Alright. I'm not grading stuff. There comes your labs. Please. Okay. Alright, good deal. Labs. Okay, sounds good. Thank you. Thank you, Alex.
That's the equation for that. But you're always wrong.
4,000.
No, I didn't. Oh, yeah.
Where's your version?
Hmm?
Where's your version?
Well, that's what the original did, so.
So you multiply square, which is this. That's the equation.
What do you think, you know? Yeah, that was the same one. The first one I just did it wrong. Okay, well, it could be First one did this, equals, divided by.
You know, volume is is that
Don't ever doubt me. So you doubt
So
me.
what number is
I
it?
doubt myself.
So what do you do?
That's it.